Okay, so this week we've been looking at generalized least squares and also Boxcups. So what we're going to do today in our case study is we're going to have a look at an example of Boxcups. So let's load some packages as always. I don't actually need tidy models. That's just for next semester's course. So we've got this data called FEV. What it is for a variety of subjects, we've got an ID. We've measured their age, their lung capacity by FEV, which is forced expiratory volume. Basically, you take a big deep breath in, and you blow out, and we measure basically how the volume of the air you blow out. We have height, gender, and whether you smoke or not. Okay, so let's start with some exploratory data analysis as always. So let's have a look at what we've got here. So altogether we have 654 subjects and we have 6 columns. 2 of the columns are character, so that will be the sex and smoker, and the rest are numeric. With the sex and the smoker, they're all complete, no missing data. There's 2 unique levels for each of those. So with sex, we just have male and female. For smoking, we have non-smoker and smoker. ID is just a number. I mean, you could actually treat ID as a factor because it's just a label of the individual people. Age is numeric. In fact, if we just move this across and rerun this, so we can see it lined up. So age, we've got a mean of 9.93, standard deviation of 2.95. Obviously, again, we have min, Q1, Q3, median, max, and we've got our little histograms of them. We've also got force capacity and height. So we're getting used to this. The first thing I'm going to do is I'm going to have a look at my response variable, because what we want to do is we want to be able to predict lung capacity. So here we are. There's a couple of peaks, but so maybe we've got 1, 2, 3, maybe trimodal, but you could argue maybe unimodal. A little bit right skewed. Definitely some amazing lung capacity up here. So the thing I'm going to do is I'm going to grab all my response variable, FELV, and the 2 categorical variables. I'm going to pivot this longer like we've done before, and then I'm going to put this into box plots. So here we've got the box plots of male versus female. We seem to have that the median is slightly higher for males, so males have slightly higher lung capacity, but not really obvious. The surprising thing here is we find that if you're a current smoker, you have a higher lung capacity than if you're a non-smoker. Does that make sense? Does it pass the stability test? Have a think about it. We're going to come back in this course to this data set and answer the question of why does smoking increase your lung capacity? So, interesting if you think about it. I'm not going to focus on that today. Now I'm going to do the same with the numerical predictors I care about, age and height, pivot longer, ggplot. So let's have a look at this relationship. So we basically see as you get older, your lung capacity increases. Makes sense. As you get taller, your lung capacity increases. Notice there's a slight curvature here. It's subtle, but if you look carefully, you can see a slight curvature. But in both cases, we've got a positive slope. So what we're going to do is we're going to start a very simple linear model. We're going to look at the lung capacity, and we're going to use height, sex, smoker, and age as our predictors. And then we're going to look at our assumption plots. And you see we've got some problems here. Let's start looking at the first one, residual versus fitted. Notice we've got this curvature, which to some extent I did note before, remember. I said, oh, we've got some curvature. There's definitely some curvature there. But also we have a violation of homoskedasticity. Notice this gets more spread as we increase our fitted values. We can also see this, in fact, what you see when you look at your standardized residuals versus fitted, you have a drop down in the amount of variability and then it increases again. So we have some heteroskedasticity there. So the thing we could do before we go any further is we could say, well, we've found these problems. Why don't we look at doing a transform of FEV? Okay, so how could we do that? Well, we're going to use Boxcups. So the Boxcups function, you give it a model, and it's contained within the mass library which is built in. So if I run this command, what it does is it's given us our likelihood. This is our log likelihood. This line is the maximum likelihood estimator, so that's the value you should use. But these are your 95% confidence intervals for that value. So what we can do here is the true value is, say, about 0.1. But as I said, what we have to do is we look for one that makes more sense. And you can see that 0 is contained within the 95% confidence interval. So if you remember from the lectures, if lambda equals 0, that's equivalent to taking a log. So what he's saying is you should consider taking a log transform. Well, let's do that. Let's now fit exactly the same thing, but now we have a log. And we'll have a look at our assumption plots once we've done that. And now things are looking a lot better. You can see we've still got a little bit of deviation from normality. This might not be the only adjustment we make. But if we look at this plot, look at how this now, the curvature seems to have disappeared. It looks very equal. It's also equal. So there's a really simple idea. We fitted our model. Our first fit, we noticed there was violations of our assumptions, so we need to do something about it. So we quickly passed it through Boxcups. That said, lambda equals 0 is a good transform, so we took the log, and now I think it looks a lot better. Now we can start exploring and seeing what that shows. So there you are, a very simple example of using Boxcups. See you next time.